Hello, everyone, and welcome back to lecture two of the electronics module, where we will be talking about analog electronics, i.e., amps and filters. Okay. So, by the end of this lecture, we should be able to describe the properties of an ideal operational amplifier, which is the op amp, calculate the gain for inverting and non-inverting amplifier configurations, explain the role of a voltage follower, a buffer, and impedance matching, describe how a trans-impedance amplifier converts photodiode current to voltage, calculate the cutoff frequency of a passive RC filter, and distinguishing low-pass, high-pass, and band-pass filter behavior. So we'll cover our recap, then our op amps, then our op amp configurations, our passive RC filters, our active filters, our worked examples, and our summary as usual. Okay, so quick recap. Remember from last time, we were looking at taking analytical signals to the electrical domain. We were looking at taking transducers and using those to convert our physical or chemical signals into an electronic signal. But remember, we had to use also our DAC chain. We had a transducer. We had to condition our signal. We had to change our analog signal to a DC signal, and then that passed to the computer. Don't forget our passives, our resistors, our capacitors, and our inductors. And so we also encountered two or three laws, Kirchhoff's current and voltage law, and also Ohm's law. Okay, so remember about those. Today, we're going to be looking at using transducer signals and making those stronger using amplification. And then we'll be learning how to filter those and making sure that our signals are ready for reading. Okay. So what is an operational amplifier? An operational amplifier or op amp is a high gain differential amplifier. That's a mouthful. So let's have a look further. So look at the symbol on the left. It's going to be a triangle with two inputs and one output. The minus sign marks the inverting input and the plus sign marks the non-inverting input. The op amp amplifies the difference between these two inputs. The equation then is V out equals A sub OL times the quantity V plus minus V minus. And there's a critical number here, which is A sub OL, the open loop gain, and is typically 10 to the fifth or sixth. That means even a microvolt difference between the inputs produces volts at the output. That's far too much gain to be useful in its own, which is why we always use op amps with negative feedback. We connect the output back to the inverting input through resistors, and those resistors determine the actual useful gain. The name operational comes from their original use in analog computers, where they performed mathematical operations, addition, subtraction, integration. Today they're everywhere. Every instrument you've studied has op amps inside. So let's go and have a look at our ideal op amp before we look at specific configurations. So this is a simplification that makes circuit analysis straightforward, and it's remarkably accurate for most instrumental applications. The table on the left shows 5 ideal properties versus typical real values. Infinite open loop gain, infinite input impedance, zero output impedance, infinite bandwidth, zero offset. Real op amps don't quite hit infinity or zero, but they come close enough that the ideal model works. Now, the most important thing on this slide is this box at the bottom, the two golden rules. These only apply when negative feedback is present, which is always the case in the configurations we'll study. Rule number one, no current flows into the input terminals. The input impedance is so high that we treat it as infinite. The inputs draw zero current. The second rule then is the op amp adjusts its output to make V plus equal V minus. These two rules are all you need to derive every gain equation we'll see today. On the right-hand side, I explain what these properties mean practically. Infinite input impedance means the op amp doesn't disturb the signal it's measuring. Zero output impedance means it can drive any load, and the concept of a negative feedback, connecting output to the inverting input through a resistor, is how we trade that enormous raw gain for stability and predictability. Okay. So the inverting amplifier is the most common op amp configuration. So we look at the circuit. The input signal comes through Rin to the inverting input. The feedback resistor RF connects the output back to the same point. The non-inverting input is grounded. The gain equation is beautifully simple. V out equals negative RF over Rn times V in. The gain depends only on the ratio of two resistors, not on the op amp itself, not on the temperature, not on the signal frequency, just two resistors. That's why op amp circuits are so reliable. The negative sign means the output is inverted, flipped in polarity. If the input is positive, the output is negative, and vice versa. This is just a 180-degree phase shift. It doesn't lose any information. But we also have to look over at the red dot labeled the virtual ground. So this virtual ground, um, so the inverting input is at 0 volts. It's not physically connected to the ground, but it behaves as if it were, and that's the virtual part. So at the bottom we have an example with RF equaling 100 kiloohms and Rn equaling 10 kiloohms. The gain is negative 10. A zero point 0.1 volt input becomes negative 1 volts at the output, okay? So if I wanted a gain of negative 50 and my Rn is 2 kiloohms, what RF do I need? The answer would be 100 kiloohms. The non-inverting amplifier then. This non-inverting amplifier has the signal connected to the non-inverting input, the plus terminal. The feedback network of RF and R1 connects between the output and the inverting input, with R1 going to the ground. The gain is 1 plus RF over R1. Notice two things. First, there's no negative sign, so the output is the same polarity as the input. And second, the minimum gain is 1, where RF is 0. You just get the input back. This configuration cannot attenuate, and the biggest advantage here is at the input impedance. Because the signal goes directly to the op-amp's non-inverting input, the circuit presents an extremely high impedance to the source, and this means it doesn't load the signal, which is ideal for amplifying signals from high impedance sources. In the example, RF equals 47 kiloohms and R1 equals 10 kiloohms, giving a gain of 5.7. A zero point 0.5 volt input becomes 2.85 volts. So the next one then is the buffer or the voltage follower. So this is a special case of the non-inverting amplifier where RF is 0 and R1 is infinite, meaning the output is connected directly back to the inverting input with no resistors at all. The gain is exactly 1. V out equals V in. So why is this useful? It seems like it doesn't really do anything. The answer then is in impedance matching. The input impedance is going to be massive, on the order of 10 to the 12 ohms. The output impedance is nearly 0. The voltage follower acts as a buffer. It copies the voltage without drawing a current from the source and without losing voltage to the load. So this is a classic example. This classic example is the pH meter. A glass pH electrode has an internal resistance of about 10 to the 8 ohms, which is 100 mega ohms. If you connect that directly to a voltmeter with, say, 10 mega ohms input impedance, you'll lose 90% of the signal through voltage division. But put a follower between them and the full electrode voltage passes intact. So we can continue on. So the transimpedance amplifier or the current to voltage amplifier. So this is probably the most important op-amp configuration for analytical chemistry. The transimpedance amplifier converts a current into a voltage. So look at the circuit. A photodiode is connected to the inverting input. The feedback resistor RF connects the output back to the same node. The non-inverting input is then grounded, and here's how it works. The photodiode produces a photocurrent IPH. By the golden rule number 1, no current flows into the op-amp. So where does the photocurrent go? It must flow through RF. Because of golden rule number 2, the inverting input is at the virtual ground, so V out equals negative IPH times RF. The output voltage is directly proportional to the photocurrent, which is directly proportional to the light intensity, which is related to the analyte concentration through Beer's law. So this is the entire signal chain of the UV spectrometer in one equation. So in the example, a photodiode producing 2.5 microamps through a 1 mega ohm feedback resistor gives negative 2.5 volts. We've converted an unmeasurable microamp current into a perfectly measurable voltage. This current is inside every UV vis spectrophotometer, every fluorescence detector, and every instrument that uses a photodiode or PMT. When you see detector in an instrument block diagram, there's a transimpedance amplifier in there. So the summing amplifier then is an extension of the inverting configuration. Multiple inputs, each through its own resistor, connect to the inverting input. The op-amp sums the weighted inputs. V out equals negative RF times the sum of V1 plus R1 over plus V2 over R2. If all resistors are equal, it's a simple run, simple sum. If they're different, each input is weighed differently. This is useful for combining signals of different magnitudes. In instrument summing amplifiers are used for background subtraction. You invert a reference signal and add it to the sample signal to cancel out the baseline. They're also used in multi-channel detectors and signal averaging circuits. I'm never going to ask you to drive this one, but you should understand the concept here, where multiple inputs, weighted summation, and virtual ground at the inverting node. Okay. So let's summarize these. So we have five configurations that we've covered in the slide, and this is a pretty useful reference. So the key decision tree is the choosing a configuration. So do we need an amplifier voltage? We use an inverting or non-inverting. Source as high impedance, use non-inverting or a buffer. Detector produces currents, transimpedance. Need to combine signals, summing. Okay. So remember the common thread. In every case, the gain is set by external resistors, not by the op-amp. The op-amp provides the engine, the resistors set the gear ratio. This makes the circuits predictable, stable, and easy to design. Okay. So moving on then, from op-amps, we move to our filters. So why do we need filters? The issue here is noise. We've dealt with noise all the way from module one, and we know that every real signal is going to be contaminated. Power lines radiate 60 Hz electromagnetic fields that get picked up by cables and circuits. Nearby computers and phones emit RF interference as well. Resistors and transistors generate thermal noise just by being at a temperature above absolute zero. Mechanical vibrations shake optical components as well. So that's what I talked about before. Whenever you see the change of classes or people slam the doors or bang things on the desks, that creates noise and that can create problems. So all of this noise gets added to your analytical signal. If the noise is big enough, it drowns out the signal you're trying to measure, reducing sensitivity and precision. The solution here relies on a key insight. The analytical signal and the noise often occupy different frequency ranges. Look at the diagram on the right. The signal is slow with a low frequency. The noise is fast, high frequency. If we can pass low frequencies and block high frequencies, we keep the signal and reject the noise. And that's ultimately how a low pass filter works. It does this because of the frequency-dependent behavior of capacitors that we discussed in Module 4, Lecture 1. Capacitor impedance drops as frequency increases, and that's the physics behind filtering. Okay. So if we look at a low-pass filter, so this is an RC low-pass filter circuit, it's remarkably simple. A resistor in series and a capacitor to ground. The output is taken across the capacitor. The cutoff frequency is Fc equals 1 over 2 pi Rc, and this is the frequency at which the output drops to 70.7% of the input, the so-called negative 3 dB point, 3 decibel point. So let me explain this in terms of the physics. At low frequencies, the capacitor's impedance is very high. Remember, X sub C equals 1 over 2 pi Fc. So when F is small, X sub C is huge. So the capacitor looks like an open circuit and the signal passes straight through to the output. At high frequencies, X sub C becomes very small and the capacitor looks like a short circuit to the ground. The signal gets shunted to ground before it reaches the output, so high frequencies are attenuated. The transition between passing and blocking happens around Fc. The roll-off is negative 20 decibel per decade, meaning that for every tenfold increase in frequency above Fc, the output drops by a factor of 10. So we can have a look here at the frequency response of a low-pass filter. So the horizontal axis here is the frequency in log scale, expressed as multiples of Fc, okay? So this then, the vertical axis is the ratio of output to input voltage. In the pass band, the blue shaded region below Fc, the ratio is close to 1 and the signal passes through essentially unchanged. At exactly Fc, the output drops to 7.07, which is negative 3 dB point, and that's our cutoff. Above Fc, the curve drops steeply. At 10 times Fc, the output is about 10%. At 100 times Fc, it's about 1%. This is the attenuation region. So if your signal is at 1 Hertz and your noise is at 60 Hertz, setting Fc to 10 Hertz would pass 100% of our signal while reducing the 60 Hertz noise to about 16%, which we'll calculate exactly in a worked example later on. Okay. The opposite then is a high pass filter, and it uses exactly the same components as a low pass, one resistor and one capacitor, but their positions are swapped. The capacitor is in series and the resistor goes to ground. The cutoff frequency formula is identical. FC equals 1 over 2 pi RC, but the behavior is reversed. Frequencies above FC pass through, frequencies below FC are blocked. At high frequencies, the capacitor's impedance is low, so the signal passes through easily. At low frequencies, the capacitor blocks the signal. The main application in analytical instruments is removing DC offset or baseline drift. If your detector's output slowly drifts over time, that's a very low frequency signal, essentially DC. A high pass filter removes it while passing your actual amplifying analytical signal. And this is also called AC coupling. So, what happens if you want to pass a specific range of frequencies and reject everything above and below? That's the band pass filter. And make one, you can make one by cascading a high pass filter with a low pass filter in series. The high pass removes frequencies below FC1. The low pass removes frequencies above FC2. What survives is the band between FC1 and FC2. Look at the plot on the left. So the dashed blue line is the high pass response. The dashed red line is the low pass. The solid blue curve is their product. The combined band pass response, it peaks in the middle and falls off on both sides. The most important instrument application is the lock-in amplifier, which we'll discuss in probably lecture 4. It modulates the source signal at a known frequency and uses a very narrow band pass filter to extract only that frequency, rejecting all of their noise. It's incredibly powerful for pulling signals out of extreme noise. The taxonomy at the bottom right summarizes all 4 filter types: low pass, high pass, and band reject. You should be able to describe what each one of these does. So what happens if we make active filters, which is a combination of our hop amp and RC? These passive RC filters do have their limitations, and the output is always smaller than the input. They can only attenuate. When you cascade multiple stages, each one loads the next, degrading performance, and the roll-off is gentle at negative 20 decibel per decade. Active filters solve all of these problems by incorporating an op-amp. Look at the circuit on the right. It's an inverting amplifier with a capacitor in parallel with the feedback resistor. At DC and low frequencies, the capacitor is an open circuit, and the circuit acts like a normal inverting amplifier with gain RF over R1. As frequency increases, the capacitor's impedance drops, reducing the effective feedback impedance and therefore the gain. Above FC, the gain rolls off. So this single circuit both amplifies and filters. The cutoff frequency is 1 over 2 pi RF CF, and the DC gain is negative RF over R1. The buffer property of the op amp also means you can cascade active filter stages without loading effects. And by choosing a specific component ratio, engineers can achieve much steeper roll-offs. Butterworth and Chebyshev designs give negative 40 or negative 60 decibel per decade. In practice, most modern instruments implement filtering digitally after the ADC, but the analog active filter is still used as an anti-aliasing filter before digitization, which we'll discuss in lecture 3. Okay, so let's tie this all together with a worked example on an amplifier for a fluorescence detector. So a fluorescence detector's PMT produces a photocurrent of 0.5 microamps at the analyte's emission wavelength. We need to convert this to a voltage suitable for the ADC, which accepts 0.0 to 5 volts. Step 1 then is we need to convert the current to voltage using a transimpedance amplifier. So we choose the RF so that the maximum expected current, say 5 microamps at the highest analyte concentration, gives 5 volts. And then we follow the equation. Step 2 then is to calculate the output voltage for the sample. So for our actual sample, the current was 0.85 microamps, and the transimpedance output is negative 0.85 microamps times 1 megaohm, which gives us, which equals negative 0.85 volts. So notice the negative sign, the input has been inverted. Then the third stage will be asking the question, do we need to do further amplification? We added a second stage, an inverting amplifier. We choose RF equals 47 kiloohms and Rin equals 10 kiloohms, giving a negative 4.7 gain. The output becomes negative 4.7 times 0.85, which equals positive 4 volts. The double inversion restores positive polarity, and the signal is within the ADC range. This is the real two-stage signal chain. Stage 1 converts current to voltage, Stage 2 amplifies and reinverts. This exact architecture is inside fluorescence spectrophotometer. Our second Our second worked example is a gas chromatograph's FID, which produces a signal that changes slowly. Chromatographic peaks span seconds to minutes, so the signal bandwidth is less than 1 Hz, but the signal is contaminated with 60 Hz power line noise and higher frequency RF interference. We want a low pass filter with a cutoff of 10 Hz. This is comfortably above the signal bandwidth, but well below the noise frequencies. So step one is to choose a practical capacitor. Let's use 1 microfarads, which is common and inexpensive. Calculate R, so R equals 1 over 2 pi C, 2 pi F C C. Plugging in the numbers, we'll get a value of 15,915 ohms, which we'll round to the nearest standard value, which is 16 kilo ohms. Okay. So how do we actually verify this filter removes the noise we care about? And so that's what step 3 is about. So that's verifying the attenuation of the noise. So at 60 Hertz, the transfer function gives us V out over V in equals 1 over the square root of 1 plus 60 over 10 squared. And so this indicates to us that the noise is reduced by 16.4% of its original amplitude. Therefore, 83.6% has been removed. At 1000 Hertz, we get 1 over root 10,001, which is 0.01. RF interference is reduced to 1%, which is effectively eliminated. Meanwhile, our analytical signal at 1 Hertz, the transfer function gives 1 over root 10.01, which is 0.995. The signal passes through with less than 1% loss. The filter works precisely as intended. Okay. So let's summarize everything in our key takeaways. So we've learned that op amps are controlled by external resistors via negative feedback. The two golden rules, no input current, V plus equals V minus, are all you need for current analysis. The inverting amplifier gives gain of negative RF over RN. The voltage follower provides impedance matching in with unity gain, and the transimpedance amplifier is the heart of spectrophotometric detection, converting photodiode current to voltage. For filters, RC filters exploit frequency-dependent capacitor impedance. Low pass passes slow signals and blocks noise. High pass removes DC drift. Band pass selects a specific frequency range. The cutoff frequency for both is 1 over 2 pi RC, and the connection to earlier modules is seen through its ability to trace the full signal chain of the UV-Vis, the photodiode, transimpedance amplifier, ADC, and the first 3 blocks that we covered today. Okay. We'll look forward to lecture 3, where we'll learn about digital electronics and data conversion. And make sure to read up on the concepts from today and to make sure you practice all of the practice questions and read the textbook sections which are relevant to this. Okay. So remember, these are the practice problems. Please have a go at them before I post the solutions. Any questions, you are welcome to contact me or leave a comment down below. Thank you very much.